Hi there, welcome back to the channel. Let us now consider electric field due to a uniformly charged ring at an axial point. We have already seen how charges can be distributed on a straight line and electric field at a point due to the distribution of charges on that straight line. Now we want to see if charges were distributed around the ring, what is the electric field at a point P, which is on the axis of the ring, on the axis of the ring, and how we can find the electric field due to that to a small element of charge on the ring. Does that make sense? Okay, so a ring of radius A, that's the problem, says a ring of radius A has a uniform positive charge per unit length. So it has a radius A, so we are supposed to, this radius is going to be A, all right, and a uniform charge per unit length. So the charge per unit length is uniform. So remember that lambda is our the notation for charge per unit length. It says is uniform with a total charge Q. So the total charge on this place, on this ring, is Q, but that Q has been distributed uniformly into tiny, little tiny bits of charges here, and our charge per unit length is given by Q per length, right? What is the length of the circle? Remember that the orientation of this thing, or the configuration of our ring, is in the Z plane, okay? So our ring, if I turn this ring, it will face you in this way. Right now, it's currently in this axis, into the board and out of the board. Does that make sense? Then up and down. That is Z plane, okay? So this guy is a circle. That's just to show you that it's a circle, and a circle, the length around the circle is going to be 2 pi r. Does that make sense? In this case, our r is radius A. Does that make sense? So we say 2 pi A. So this will be charge per unit length. That will be Q per 2 pi A. Q over 2 pi A. All right. Then the next thing to talk about is, okay, so that's just the formula for the charge per unit length. It now says to calculate the electric field at a point P on the axis of the ring, okay, at a distance x. Okay, so this is at the distance x. So the distance from here to here is x from the center. So we have to calculate the electric field at this point E, okay? We know that the electric field is going to be pointing in this direction here, all right? So E field is going to be pointing in this direction. And so here is going to be angle theta. This is going to be angle theta as well, okay? Then we draw our normal. I just wanted to put that there. We're not doing anything yet. Okay, so the first thing to do is to set up the system. And we have set it up according to this question. It has been set up for us. So the distance from here to here, we'll call it R, okay? Now, if that's the case, then the next thing to do is now to parameterize a small element of charge here. Let's call it dq. So our dq there is our small element. dq is given by, now remember that due to, if we want to describe the charge per unit length, the charge density on this point, dq is going to be, our lambda is going to be dq dl, okay? dl here is because of the small length of this thing, okay? dl, where dl is the length of the tiny arc, that is formed, right? The tiny arc, or infinitesimally small arc. That's what I mean by tiny, exactly. Length of arc of our small element. Is that okay? Do you remember that the first thing we did after the setup was to parameterize this small portion, a very tiny portion. So that portion is going to be the dq, and we will be defining the charge density, which is uniform according to the question. With respect to that dq, is going to be dq by dl. I hope this makes sense. Okay. Now, there's something else I need to show you. Now, you remember in circular motion that if I pick a point, this is my center, if I pick an arc, a portion of my arc, for example, from here to here, and I say find the length of this arc. Remember that I could bring this here, and this would be my r, my radius, and this would be my theta, yeah? Okay? If I wanted to find the length of arc, remember that the formula for length of arc is also theta r. Does this make sense? Okay. So this parameterized portion is going to be having a tiny little bit of angle, which we'll call d phi. Okay, it's going to have a tiny little bit of angle, d phi. So that tiny angle, d phi, is going to be this our guy here. So that phi will be equal to the length of the arc over r, right? I mean theta, according to this equation, will be s over r. So our d phi 2, that will be the small angle there will be equal to the length of the arc. The length of our own arc is dl. So that will be dl over, what is the radius? The radius will be a. Okay. All right. I just tried to use the mathematics to show you what I'm trying to derive. All right. So we have this, we have this, we have this. So let's call this equation 1. Let's call this equation 2. Let's call this equation 3. We don't know where we know where we are heading to at the end of the day, but let's see what we can make of this first. Now, you know that our lambda is q over 2 pi a, yeah? Okay? And the same lambda is the q dl, okay? Now, we can therefore say that our dl, our dq from there, from equation 2, dq will be equal to lambda dl, right? Okay, so if that is the case, dl is a d phi, right? So it means that dq will be equal to lambda, since dl is from here, dl will be a times d phi, right? So our dq will be lambda dl, which is now a d phi. Okay, the comma here signifies multiplication. Okay, so d phi, dq will be equal to this, right? So recall already that this guy is q over this. That is from 1 now, from equation 1. We now know that dq will be equal to q over 2 pi a d phi. 2 pi a times a, dot a dot d phi. All right, so a can take care of a, then dq will be equal to d phi over q d phi over 2 pi. All right, so let's hold this as our equation 4. Okay, we have equation 4. Now let's recall, as we want to, find the electric field due to that point now. Recall that electric field due to a tiny amount of charge is given by the E sub E is equal to 1 over 4. No, E is equal to 1 over 4 pi epsilon naught dot dq over r squared. We already used this formula in the first equation, right? Now let's now resolve our electric fields. Now the electric field here is going to be the sum of electric field due to, our sum of electric field is going to be electric field due to x component and electric field vector due to y component, okay? Now if you look at this very well, the electric field in the y component is going to cancel out. Electric field E sub y becomes 0. Why? Because for every d phi, for every dq rather, at position phi up there, let's say for every tiny amount of charge dq at position phi. We have in the opposite direction, or in the direction of plus pi, that is plus 180 degrees. If you go 180 degrees away from pi, you'll see another similar charge, since the charges are, dq is evenly distributed. So you will see another dq that is going to be equal in magnitude to the dq at first position, position phi, but will be in opposite direction. So which means that the q in both places will cancel each other out. I hope that makes sense. I said that for every dq at position phi here, for example, as position phi here, you are going to have, if you go 90 degrees back here, you are going to have a similar charge, but that is opposite in direction. So it's going to lead to what? Symmetry. So that symmetry trick helps us here again, and E sub y component gives us 0. Okay? Then that means that the total charge, the total E is going to be the what? The E sub x component alone. So E sub x component is equal to, now how do we get the x component? We're going to resolve this to the x-axis. And when you resolve it, it's going to be closing this angle, right? Our E vector will be closing that angle. That becomes E cos theta. So that is E cos theta. So dE sub x is equal to dE cos theta. Okay? So, and dE is already this, right? Okay? Sorry, dE. dE is already that. So we can now say that dE sub x will be equal to dE, which is 1 over 4 pi epsilon naught dot dq over r squared, then dot cos theta, not cos phi, cos theta, okay? Now, remember that cos theta from here, want to remove that trig guy. Cos phi, cos theta rather from here, will be equal to adjacent over hypotenuse. And what is our adjacent here? Our adjacent is, these are two angles, our adjacent will be here, x over hypotenuse r, okay? So if that's the case, then we have 1 over 4 pi epsilon naught dot dq over r squared dot x over r. This becomes 1 over 4 pi epsilon naught dot x dq over r cubed. By the time you multiply this by this. And remember that the value of r here, also using Pythagoras theorem, the value of r, recall that the value of r is going to be the square root, that is r squared equal to this squared plus this squared, right? So that will be x squared plus a squared. So this is our r, or simply say x squared plus a squared all to power half, right? Okay? So by the time we substitute that into the equation, when we substitute that into the equation, we have our dE sub x will be equal to 1 over 4 pi epsilon naught dot x dq all over our r cubed. Now is all of this thing, all cubed. So that will be x squared plus a squared all to the half and all to 3, to power 3. Okay? Now, no, I will not advise us to substitute yet. Either ways, let's substitute. Just that we're writing too many things, so let's not substitute yet. So let's still leave it as r cubed. There's something else that we still have to do. We have to remove dq and this d by integration, right? So we're going to integrate here and integrate here. So by the time we integrate, our dE sub x will be equal to 1, E sub x, by the time you integrate the guy, E sub x will be equal to 1 over 4 pi epsilon naught. Then this guy, dq, now we are going to be integrating is, you know, it's not an indefinite integral. It's a definite integral. We are going to be integrating between 0 and 2 pi. Now, why are we integrating between 0 and 2 pi? If our small element, dq, starts at points, at a particular point, that point will be 0. By the time we integrate around the circle, we would have gone 2 pi, that is 360 degrees, yeah? So that's why we're integrating between 0 and 2 pi. By the time we integrate this, we're going to get E sub x, or E, which is the sum of x component, equal to 1 over 4 pi epsilon naught x dot x over r cubed dq. Okay? No, we want to, okay. We will substitute this guy into this equation. Okay. That's what we want to do, because we want to use angles. We want to different, before we integrate, we want to integrate in terms of angle. So recall that dq is this, right? So if that's the case, then our integral between 2 pi, 0 and 2 pi is dEx is equal to 1 over 4 pi epsilon naught integral between 2 pi and 0 of x dot, our dq is now q d phi over 2 pi r cubed. Okay? 2 pi r cubed. That's our dq. Okay? So by the time we do this, we'll now have integral of 2 pi of the E sub x equal to 1 over 4 pi epsilon naught integral between 0 and 2 pi of x cubed 2 pi, now over, let's substitute, 2 pi over x squared plus a squared all raised to the power half, then all raised to the power 3 d phi. Okay. So from here, I know that integral of the E sub x will be equal to 1 over 4 pi epsilon naught integral of, now we can separate, this guy is also going to be a constant, right? This is going to be a constant. So let's bring it to this side. Let's bring it to that side. If we bring it to this side, it becomes 1 over 4 pi epsilon naught dot into bracket x squared plus a squared. This multiplies half to give us 3 over 2. 3 over 2, then dot, or integral of between 2 pi and, between 0 and 2 pi of x cubed over 2 pi. X is also a constant, so let x come here. So we have x here. We have x there. Then q over 2 pi. Q over 2 pi d phi. Right. So by the time you integrate this, you are going to get because Q will not be affected by your integration, right? So Q will come here too. So we have integral of the E sub x equal to Qx over 4 pi epsilon naught x squared plus a squared all raised to power 3 over 2 integral between 0 and 2 pi of 1 over 2 pi. Okay, phi. All right. So if you integrate this, because you are integrating between 0 and because you are integrating between 0 and 2 pi, this is also a constant. You know it doesn't affect it. So it's more like, it looks like what we have is integral of the E sub x. I'm just trying to be careful not to make any mistake. E sub x and qx 4 pi epsilon naught x squared plus a squared 3 over 2. Now let's bring this guy here, that's 1 over 2 pi integral of the phi. Yeah, this is what I wanted to achieve, sorry. I wanted to be sure which one I'm bringing and which one I'm not bringing, because we are integrating angles. Is that clear? And this is an angle here, so this constant is unaffected. So if you integrate between 0 and 2 pi, that's just saying, that's just like, I don't want to rewrite this. So this thing here is equal to, integral of this, the phi is going to be 2 pi minus 0. Does that make sense? So we're left with 2 pi. Exactly, that's what you are going to end up with. Okay, so our answer now becomes, by the time we integrate this, then we'll be left with E sub x, or E, equal to Qx over 4 pi epsilon naught x squared plus a squared all raised to power 3 over 2 dot 1 over 2 pi. Then this has become 2 pi, so times 2 pi, so this takes care of this. All right? Good, so our final answer becomes Qx over 4 pi epsilon naught over x squared, times all raised to power 3 over 2. That's all. So that is how to find the electric field due to a uniformly charged ring at a point, an axial point, point P. All right, so that is our answer. Do have to subscribe to the channel. In the next one, we're going to find how electric field is, how to find electric field over a surface, electric field of on due to charges distributed over a surface. Thank you.